video. Did you guys hear that? I don't know. Okay. The old meeting now. Okay, so a late start, but whatever. At least we're recording now. Okay, so take f of x and g of x equaling this one, and then we were like, okay, so the next evolution of the process would be this maybe. Here's another thing to consider. What if we did this? And we were like, let's see, should we do f compose g? Let's do, this will be weird, but you'll love it. F compose g again, but not evaluated at a particular value. It's f compose g of x is what we got to figure out. Or I shouldn't even say evaluate. It's like simplify or something, just whatever. Let's figure that out. And so what's different about this though, guys, as you'll notice, is that if we say f compose g of x, we're essentially saying, like if we were to do it the same way as we did last time with the value, the particular value in there, we're saying let's plug x into g, and then that answer goes into f, you know? It's the same old thing. But x plugged into g is what we already have. Like these are functions of x already. They're already in terms of x. And so if I have x plugged into g already, that means basically just forget this first part, leave it looking like a function of x and plug that whole g of x function into f. Or in other words, remember, another perspective on that from before is it means this is f of g of x. Or in other words, the whole stinking g of x function without anything plugged into it, just still in terms of x, that whole stinking g of x function that we're looking at already, x plus 2 squared, that whole thing plugged into f. That's what f compose g of x is. And so we'll take the g of x, x plugged into g, or in just g of x, shoot that whole stinking thing still in terms of x into the f function. And that's how she rolls. And so let's see here. What if we said, okay, well, let's g plugged into f, so it'll look like an f function with something plugged into the f, because this first part is kind of done. G plugged into x is done. Then that answer of g of x, which is x plus 2 squared, we're going to plug that into f here. And so we'll see how that goes. Here we go. That means it'll look like 4 minus 5, 5 times something. And that something is what the g of x is. That's where g goes. 4 minus 5 times something. That's what f of anything is. And then we'll go x plus 2 squared plugged in there. And then we just got to, figure it out, I guess. And so what's cool about this, guys, is in this particular curriculum, as you're getting used to this stuff, sometimes they let you just leave it in these terms, and so it might be worth just trying, like, because the idea is just to get used to how to compose functions, and simplifying them is a whole other battle that we'll be doing again today. But sometimes you can just leave it like that, because that way it still bears the resemblance of the composition. You can see that there's one function inside of another bigger function, So feel free in your answer box before you foil everything out and all that, try and enter them in like this sometimes, because sometimes it'll actually take it, and I would be okay with that, anyway. Or if it don't take it, we still do have to be good at simplifying. So if it doesn't take your answer like that, sometimes we are challenged to simplify, and sometimes there's good reason to, and so let's see if we can handle that together. Let's see if we did a 4 minus of 5 times all of that mess. Maybe we should start by foiling this thing out in the parentheses first. We have x plus 2 times another x plus 2. And then, foil, foil, foil. And let's see how that goes. 4 minus of 5 timesing with, that's x squared plus 2x plus 2x again. Whoa. Plus 4. And then I guess before we distribute that minus 5, we could maybe do the like terms thing again. So let's see here, the 2x and the 2x, x squared, 4x and 4. And then just be careful, because that is a minus 5 that's distributing, so it's minus 5 times x squared minus 5 times 4x is minus 20x. And then minus 5 times 4 is minus 20. And then I think we're pretty much good. Just maybe we'll put the last couple of like terms together as a couple of constants there. Let's see here. What's that going to be? It's a negative 5x squared. I'm going to minus 20x. And then what is the constant going to be? It's a 4, regular 4, and minus 20. Was that negative 16? Are we good there? Is this thing on? Testing.
Yeah, negative 16.
Wonderful. All right. Cool. Sick. Anyway, that's at least one take on how maybe you could approach f composed g of x if you had to figure out a composition of functions, not evaluated at a particular value, but still just in terms of x, you know. Now I have a challenge for you guys. Taking those same two functions, here, I'll even write them here again. F of x equals 4 minus 5. No. 4 minus 5x. And then g of x was x plus 2 squared. Same deal. I got challenge for y'all. Take those ones. See if you can figure out here. Let's not do that again. Let's do g compose f of x. See if you can figure that one out. And then also see if you can handle f compose f of x. Take a minute on those. See if you can jam them in there. And then I do recommend, even though sometimes in your answer book or the answer boxes, you don't have to simplify them. See if you can handle simplifying these ones. If you don't mind, try them out. Take a few minutes on that, and I'll be waiting, and I'll just be sitting here bored. Maybe I can like talk to a few of you guys and distract you while you're doing things. But you know what? Oh yes, for the sake of making the recordings less boring, I'm going to pause it here. There's a pause option, so that's good. So I'll pause it while you guys are doing it. Okay. I don't know if y'all are done or not, of course, but don't feel like you gotta be. Let's see what we can do together on this mess. Okay. Maybe talk me through here real quick. G compose f of x. You know how that's sort of starting is we'll go x into f is just f of x. And that whole thing will be plugged into g. So we're plugging the f of x into the g function. So let's see what g looks like. G looks like something plus 2, all that squared. And then if we're plugging f of x into the g function, that's going to look like a 4 minus 5x shoved into the g function. And so this in itself is already a perfect composition. It's not simplified, but it's a good composition. Answer book or whatever may take it that way. Otherwise, feel free. Let's see if we can simplify this. I don't think that we need these parentheses really, even though, you know, I put them there for emphasis, but I don't think that, yeah, I think we can just get away with like putting stuff together. So that's a minus 5x, but we have a positive 4 and a positive 2 we could put together. So it's like a 6. So that's negative 5x plus 6, or you could do 6, take away 5x. That also would be fine. And then we have to square the mess. And so if we square it, it's a minus 5x plus 6, minus 5x plus 6, or again, 6 take away 5x, both times it'd be fine. And then it's foiling time. So let's see here. If we FOIL that mess, don't let me mess this up. That's 25x squared positive because the negatives, you know. And then that'll be a negative 30x twice. Couple of negative 30x's and then a positive 36. And then let's see here, that's 25x squared minus 60x plus 36. That's what I'm getting. Are you guys getting that too? Anybody else getting that? Does that look okay?
Yeah, that looks fine.
Yeah, we're getting that all right. One person in the entire room. Thank you for communicating.
Got it, Ron.
Got it.
All right.
I didn't do that one because I got confused. Sorry.
That's okay. It's all right. I bring these things up not to make fun of you, but because I entertain myself through the process. And well, mostly just because I want to make sure you guys are still interacting, that I'm not totally losing you. You guys know that. Anyway, maybe before we go on to the next one, do you guys mind thumbs up or downing me real quick? Shoot, where's this thing gonna be? On how that last one went, because I know it was a little bit tougher for some folk. Okay. Yeah, okay. Boom, 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 boom. Cool, right on, Ray. I see that Raymundo was willing to give a thumbs up or down, but not Alex, who is clear. Oh, he's there. All right. They're like on the same couch. All right. Okay. Cool. Dig this then. Oh yeah, screen share. All right, whiteboard. All right. Then dig this. Okay. Well, that's a little weird. What looks like we're getting some sideways thumbs on that one. Maybe we'll go ahead and I had planned to practice this stuff again anyway, so that's the next round. It's a little bit more of the same kind of thing, but we have also, before we move on, F compose F of the same functions. And so in this one, let's see, this one, since they're both F, it's maybe not as bad, but it tends to be a little dizzying for people to compose a function with itself sometimes. Unless I just amazingly taught it just right. So we'll see. And so we have f of x is what it is. And then that f of x is being plugged into f again. And so let's see what that looks like. If we had f, that's 4 minus 5 times something. And then that something is also f of x. And so let's see how that looks. That something is also f of x. So that's 4 minus 5x inside there. And that's pretty much good. And then we'll simplify that the best that we can. You can leave it like that sometimes again, but then this one won't be too bad to simplify, I guess, anyway. Let's see here. Minus 5 times 4 is a minus 20. And a minus 5 times a minus 5x is a positive 25x. Looking good. From there we got, let's see here, 4 take away 20 is like negative 16 plus 25x. That's as far as that one's going. Or you could do 25x take away 16 would be fine, of course. How you guys feeling about that? Are you guys getting that same thing or no? Anybody?
Got that one wrong also.
Nailed it.
No, I got that one.
Yeah.
Okay. Okay. Here's what I have for you guys. I feel like this, it's a little bit weird to do compositions when you're not used to them. And so keep trying to move this thing. So I figure maybe before we do anything different, we could spend a few more minutes composing functions, but I had a different variation to look at. Check this out. Something that I noticed in your homework that pops up would be something like this. What if we gave you, let's take f of x equals something like 5 over x minus 2. And g of x equals something kind of weirder or something, and you're like, well, this is 3 over x, and then plus, 1 or something. These are both very fraction-y looking functions. And so it'll be a little bit weird to like compose them because they're already weird. And so that's why I wanted to like try this with you real quick. And so let's try this real quick. If we were to do something like we always do, we'll start with f compose g of x, and let's see how weird that looks. But essentially this is just going to be like, okay, let's do g of x plugged into f of x. So it'll still look like an f function with a g inside. So let's see here, g plugged into f means we'll have an f function. That'd be 5 over something minus 2. But then the something we're plugging in is g of x plugged in there. And so let's see how that looks. g of x being plugged in. Let's see here. That's 3 over x plus 1. It just looks bad. Here we go. Here's 3 over x plus 1. And then that's the g of x inside of the bigger f of x function. And as you can see, as we kind of predicted, it's a little weird just because it's kind of fraction-like. And so from there, that's where I wanted to give you my 2 cents. There's a bunch of other ways to do this, but in the past, we've sort of gone this direction with this kind of thing in our class. What if we said, well, let's just leave the 5 alone for now, I guess. But the bottom of this seems like it could use some work, you know? And if I had 3 over x plus 1 and then minus 2, seems like, well, the plus 1 and the minus 2, I don't really need the parentheses. I could probably put those together right now. So that's good. At least we don't have tons of stuff in that way, but let's see here. What's that going to be? Positive 1, take away 2. That is not plus anything. Positive 1, take away 2 is like a minus 1, I believe. And then from there, we got to like get the bottoms to match, because I feel like maybe the best thing to do at this point is to like put these bottoms together. Again, not the only way to do this. But if we were to like put the bottom stuff all together, the bottoms have to match. So I'm going to ask you guys real quick. Tell me, guys, what should I times by to make those bottoms match?
X.
Yeah, that'll work. If we just times by x on the top and bottom, that'll be good. So then let's see here. We haven't done anything with the 5. That's still just sitting there. And then both of these things are over x now. That's over x. This is over x. So that's good, because now we know it's whatever it is, it's something over x on the bottom part. So that's good. And then the tops are just whatever they're going to be. This is a 3, take away a 1x. 3, take away a 1x. And that's, I don't know, those are not like terms or anything. So we might just be stuck with saying, well, that's 3 minus 1x. Or, you know, you could put the 1 if you wanted to or not. But it's just 3 take away 1x over the x. And I, you know, oh, well, at least it's one fraction altogether now, you know, because the bottoms are the same. And that's where we run into this other issue of a complex fraction, you know. And I wanted to remind you about that. Do you guys remember this? If we were to say like, this is 5 over that other thing, 5 over that 3 minus whatever. What's another way to do that? What do you guys remember? How could we handle this?
Flip it and multiply it.
Look at that. I love it. Yeah, so that's, I think, what we've done in the past in our class. And so maybe let's go ahead and continue in that pattern. This is indeed, just like she was telling us, guys, this is 3 over, it's a 3. This, you know, being a 5 over whatever this fraction is, the little over thing also just means divide by. So I guess that's the direction we're being taken here. And so if we were to go that way with it, we could say, oh, that's the same thing as 5 divide by 3 minus x over x, or 1x or whatever. And if we think of it as a divide, then that's where we can go exactly that direction, where we're like, oh, that's, I know how to divide fractions. Divide by this just means times the upside down version. And we'll put the x over the 3 minus 1x. That way, timesing the upside down being the same thing roughly as dividing by fractions in the first place. We're looking good, except that it's hard to read what I'm writing there. But then we can just kind of like, you know, do the old fraction times thing and we'll be okay. It's supposed to say 3 minus 1x. Just, I don't know. Use your imagination. Now it looks infinitely better. Tell me, guys, 5 times x. Well, I got that one. That's 5x. And then, well, I guess there's not much to times on the bottom either. 1 times anything is just that thing. So this is just still 3 minus 1x, or just 3 minus x would be fine, really, at that point. And that's how the cookie bounces. You know, again, there's other takes on how to deal with the complex fraction, but this is maybe a user-friendly one for now. Cool. That being the case, you know, this one's obviously a little bit twisted up because it's got all kinds of fractions in it. I'm going to have you guys try one that's the same kind of thing, but we'll have you try G compose F this time. Like we've been doing, you know? And so let's see what we can do here. Same two functions. I want you to take same two functions, same F, same G. And then see if you can handle, let's see, try a minute here to do G compose F of X. See what you can do. And then I shall pause the recording. All right, guys, help me through now. Okay, let's see here. All right, G compose F of X, something about that. So G compose F, that means we have F of X, and then we're shooting that into the G function. It'll be G of that F of X. And so let's see here. G was, here, F was this. F of X was, what was it? Oh yeah, 5 over X minus 2. And G of X was the other thing. It was like X over 3 or something minus 1. Is that right? Let's see here, plus 1. I mean 3 over X. I was way off. Just don't write that down. Okay. 3 over X plus 1. Looking good. Okay. Now we had to do, what was it? G compose F this time. Goff. Like Bob Goff. Okay. That's an author, you know, I don't know if anybody's into reading, but he's the one that I would recommend. Very, very good author. I admittedly don't do a ton of reading myself because I read very slowly, but I've been trying to get some. But there's a guy named Bob Goff. It's, you know, this reminded me of it. There's a couple of really good books out there. Would recommend. His first book is my favorite. Well, anyway, who cares? And so here we go. Bob Goff of X. That's F of X, and then we'll do that into the G. Here we go. So then G of, that's going to be 3 over something plus 1. That's what G of anything looks like. And then, you know, F in there. And so let's see here. This is 5 over X minus 2. That's the F inside of the G. I guess, you know, since this thing sort of looks like an O, this is like the definitive perfect composition of functions, because look, if you were to just read this, check this out. G, it like says G of X. It's G, then it sort of looks like of, and then X. It's like written in code. This means nothing. Check this out. Okay, shoot. If you guys are noticing, maybe you run into the same thing that I'm noticing. It looks like this thing on the bottom is like just one big fraction in the first place. So I don't think there's a whole lot we can do with it, because it's like already like just been put together as one fraction. So maybe we'll start by just go ahead and do this thing where we'll, you know, write it as a divide. And so we have 3 divided by 5 over X minus 2, because the plus 1 is out there separate, you know. Maybe we'll start there. And you guys know how divide goes. That'll be 3 times with the upside down version, X minus 2 over 5. Then there's a plus 1 sitting there. And then if we take care of that, this timesing thing, let's see how that goes. That's just 3 times all that mess and 1 times 5. So the bottom, it looks like 1 times 5 is just 5. And the 1's still sitting there. But then the top, we have the 3 timesing with the X minus 2. That's sort of a distributive mess. And so let's see, that's a 3x take away 6, I guess. And then we're pretty much good. It's just that since we have to add it with the 1, let me clean that up a little bit. Since we have to add it with the 1, it's like the bottoms at that point should probably match. And so like, you know, I was gonna put 5 over 1. The 1 is over 1, this is over 5. They don't quite match. Talk to me, guys. If I were to times by something to match these bottoms, what should I times by in Baskin-Robbins colors?
5.
Yeah, we could times by 5. That should work. Then they'll both just be 5s. That's good. Cool. That's pretty cool, I guess. It's interesting, Adam. Okay, so then we'll be like just doing that. And so let's see here. That's 3x take away 6 already was over 5. Plus this is 5 over 5. Now the bottoms match. This is good. And then, whatever. Let's see, they're both over 5, so it's something over 5. And then we'll just put the tops together. This one plus that one, Let's see, a 3x minus 6 plus 5. The 3x is the only x part. And then we have minus 6 and plus 5, whatever that is. Minus 6 plus 5, I'm getting like a minus 1. Something like this, I guess. That's pretty cool, I guess. Yay! Okay. Just in case anybody is like, you just super don't want to be on the recording, I'm going to pause it for a second while I take you guys' temperature on that one. All right. Dig this then. Couple of things before we go into 5.2. And then I do actually plan on somewhere around 10 o'clock. We're just going to do this for a few more minutes. Around 10 o'clock, I do plan on giving you guys a break because it's just, I've not been good about that. And I know it's getting a little bit rough for folks. So we'll take about 10 minutes at around 10 o'clock. But a couple of things I wanted to mention real quick. Okay. One of them might be, okay, let's do this. This is a good one. Okay, dig this. Look at my cool looking chart. You don't have to do a cool looking chart, but it was coming out super ugly when I was doing it freehand. Oh no, whatever. So I decided I would start using cool straight looking lines to make it look a little better. But they're not perfect right angles or anything. Okay. What I got going on here, guys, is a chart keeping track of inputs and outputs of a function. And we'll be reviewing to this kind of thing in 5.2 as well. What I want you to do is, oh, here we go. What the heck is that about? Okay, let's undo that. Okay. Oh, yeah. All right. What I want you to do is we're going to keep track. This is like, usually we have an X and then there'll be a Y or something, right? But since we're talking functions, we'll say this is X and then f of X. Or in other words, X, these will be the input numbers, in, and then these will be output numbers for f of X. And then there's a third thing that we'll be talking about in a second. And so let's just talk about, any given function will be like inputs, and it's a little chart like we do. And it's like 1, 2, 3, 4, 5 different numbers we could put into the function. And then we'll see what kind of numbers are coming out of it, And so let's see, if we said, what if we were just like, well, this is a 3, 4, 5, and then 1 and 2, say it's an onto type function, 1-to-1. Sort of before we even fill in the third part of this, what's going on with this, guys, is we're like saying, well, if I plug in a 1 into my f of X function, guess what the output is? It's 3, So I plug in a 1, I get 3 out, just like we're used to getting. So then, or else you could say something like f of 1 equals 3, or if you plug a 1 in, you get a 3 out when we're talking about f function. But also, we now have a g of X also output chart to organize. And so also the outputs, if you were to plug these same X's, same inputs into the g function instead, maybe you would get different outputs because it's a different function. And so let's do 5, 4, 3, 2, 1 or something. I don't see any fixed points. Oh, yes, I do. And so I guess at that point, help me out with this one, guys. Let's see if we can read this thing. What is g of 1 going to be? Or if I plug a 1 instead of into f, but I plug 1 into g, what is the output when I plug a 1 into the g function? What do you guys got?
5.
Yeah, that'll work. Yes, and so 1, if I plug it into f, I get 3. But 1, if I plug it into g, I get 5. That's kind of how we're reading this. And so if that's the intro, here's kind of what our homework will end up looking like, having that perspective to come from which to come. What if we said something like this? We're to figure out f of sort of a composition thing here. F of G of 2. This is also known as F composed G of 2. Just they're using this notation at that point in the homework. And so F of G of 2, we're trying to figure out what the heck that is, and we might need to do that in pieces. And so let's see here, G of 2. G of 2, that's us saying, well, okay, don't worry about F yet. Let's do G of 2, or in other words, we'll plug 2 into the G function first, and then we'll do F of that, you know? And so let's see here. So again, I've put an equal sign when I guess I didn't need one yet. Anyway, so, all right, maybe, well, whatever, anyway. There would be better ways to write this, but I don't like them as much. Anyway, so G of 2, I'm plugging a 2 into the G function. If I plug 2 into G, what do I get for my output, guys?
4.
Yeah, it's a 4, which is interestingly also F of 2, but whatever. So G of 2 is 4, so I'm just arrowing it down saying, okay, that G of 2 part, that became a 4. The 4 is the answer to F, or to G of 2. The 4 is the answer to G of 2. And then we're doing F of that now. And so now that 4, that was an answer, it's also now an input number, because now we're figuring out F of 4. And then we'll figure out what that is. So then we'll look at 4 over on the X's, the input part now, and we'll plug it into the F function. So guys, tell me about this. 4 plugged into the F function, what's the output now?
1.
Yes, it's totally 1. And that's all she wrote. Yaddy yap. Cool. Anyway, this is the idea. They're going to give us a composition. We'd figure it out in pieces. Let's see if we could do another couple of them real quick. What if we had G compose F of 3? Let's figure that one out. G compose F of 3. Let's figure out what F of 3 is first. And then we'll do G of that answer. So F of 3, let's see, that means 3 going into the F function. What's the output for that? 3 into the F function.
5.
Yes, it's 5. And then we'll do G of that, G of that 5. And so we'll take that 5 is now an input number. So 5 as an input through the G function. Now what's the output there?
1.
Yes, it's totally 1. Seems like I can't get away from the ones. Cool. Anyway, this is the process we take you through in that. Anyway, what I mean to say is we don't have to do a whole lot of like practice time on this one together or anything. I suppose I could, but just due to time constraint, probably I won't have you guys do any on your own here. But I wanted to at least expose you to them. So let's do one more together. And then I wanted to talk to you about that other thing that I was, that I wanted to bring up before our break. Okay. Dig this something. Oh yeah. Let's see what we can do. What if we did F compose F of 2, F of 2. And so it's like, it looks weird, but I feel like we've gotten a pretty good perspective together in this class about that. And so let's do F of 2 first, and then we'll do F of that answer. And I think it'll be good. So then F of 2, this is the same thing as F of G of 2, isn't it? I can't get away from the ones. Oh, well, you know what? I refuse. We're not doing 2, and that's all there is to it. What should we do instead of 2? We'll start with a 1. That's what we're going to do. Yeah. All right. Okay, take me from there. What if we did F of 1? Let's start there. F of 1, let's see here. That means we're shooting 1 into the F function. What's my output there? 1 into F gives me output of, yeah, it's 3. And then we'll just do f of that 3 now, because now it's f of that answer. So then f of that 3, that means the 3 is now an input number, and we're taking that through the f function. So 3 into the f function, and then what's the output this time, guys?
5.
It's 5. Cool. And that's what we were looking for. Yeah. I don't know if you guys remember The Price is Right, but it just reminded me of Bob Barker for a minute there. Actually, they might still be doing The Price is Right, just not with Bob Barker anymore. It was Drew Carey for a while, I guess. I haven't been watching for over a decade though, so I don't know what's going on with that.
Still do carry.
Is it?
Yeah.
Well, I got that.
These kind of questions should be on the test.
Right. See, so if you don't mind, maybe just ask us about toothbrush on grout.
Yeah.
And The Price is Right on the test.
Oh, it's that one.
I love it. I just had remembered it because it brought me back to when I was younger, and I would be Bob Barker, and he'd be like, and the actual price is, and something about the inflection of us pointing to that 5, it took me right back there. So I would watch it with my grandma of all people. Anyway, if you don't mind, let's see here. Yes, okay, before we get on to the break, I wanted to talk you guys through this next deal. Check this out. Okay, take f of x equals, and then it's like all weird. It's like 70, no, why is there x there? Like 72 take away x is one variant of the problem, and then and g of x would be some other weird thing. And let's see here, okay, make sure I'm doing this well. I want to make sure I'm representing the idea right. Yeah, let's do g of x is x squared minus x. This is one variant that I've seen coming your way. And then here's what's different. Not only they're asking you to compose these things, but they might ask you this. It would be something like this. What is the domain? Dang it. What is the domain of f composed g of x? They might just say f composed g. Sometimes we shorthand it by not doing all the parentheses and stuff. What's the domain of f composed g? That's what they'll ask you for? Oh, and so one thing that you'll notice about that is you don't know what the domain is unless you know what f composed g is. So we still have to compose the function, So we'll do that real quick, and then we'll talk domain issues. So f composed g of x, let's see what that looks like. F composed g of x looks like, let's see here, that's going to be g of x plugged into f, and so let's see here, g of x shooting into the f function, I'm looking at 72 take away of, and then g of x is in it. So radical 72 take away of, and then g of x is x squared take away x. So it's weird. The function in itself, like right off the bat, you could tell this was going somewhere weird because f of x had a radical in it, and we talked about Price is Right first, so that was weird. And I feel like this is probably getting weird because of the radical, is the weirdest part about it all. And so here's what I had in mind. Take a trip down memory lane with me. It's not The Price is Right this time. What if we said something like this? Do you guys recall when we were talking about domains and I was like, okay, if we have 5 over something like x plus 2, don't write this down. Or you can, but it's whatever. Anyway, don't write this down. If we had a function that looked like this, and we're looking at the domain, what number is it that I'm thinking of that would just be super bad news right here? Some number plus 2 would just ruin things. What number does that?
-2, -2.
Yes, that's right. -2 would just straight up ruin things because that would make it like 0 on the bottom and it's undefined, Okay, so that's an issue that you run into when you see fraction-y functions. Is that the domain is restricted because you got to watch out for when it makes it undefined. That's not an issue we have here. We don't have a fraction, so there's not an issue with things going undefined. What we have, though, is a radical, and it has its own issues. There's no problem with it being 0. That's fine. -2 is bad over here because we don't want it to be 0 on the bottom. 0 on the bottom of a fraction, bad, you know? But 0 in a radical is actually fine. Because anybody, what's the square root of 0? Hot shots.
0.
Yes. And so square root of 0 is actually fine. We actually don't run into any issues unless we go less than 0. That's where things get bad. Square root of a negative, you may remember, we've talked about, and like you may have dealt with it before this class even. But square root of a negative, that's when things get bad. Not that it's impossible to deal with, but it means that we're outside of the real numbers and it's something more complicated to deal with. You know, it's not that you couldn't fix it or anything, but it gets funky. And so if we want to stay within the real number system, this is bad news for us. And so that's what I think that we'll be dealing with here, because you guys know as well as I do, this is a radical function. It has a square root in it, you know, and so it's bad news for us. And so what we might say is this: if I want to know what's the domain of this composition or of this composite function, what we could say is, well, anything's fine in the domain, but I just got to make sure that that stuff that's in the square root, this whole mess in there, I don't want it to go negative. I would rather keep it bigger than 0, or even equal to 0 is fine, but I don't want it to go negative. So here's how maybe we could approach that. And we're like, domain. We could say, take all that stuff that's inside the square root. It's 72 minus all of this mess, and it's all weird. And we could probably simplify that a little better. And then let's say, we'll just say like, well, I'd like this to stay bigger than 0. That's what the domain should look like. This is the condition, is that all the innards stay bigger than 0. Then we're not worried about going negative, you know, and that would be fine. And so that's kind of maybe the onset of the approach. And I guess as we keep mentioning, like even equal to 0 is fine. So greater than is fine, equal to 0 is fine. Just don't go less than 0. And then that opens the can of worms, because then we're like, well, what the heck? How are we going to figure this out? But we'll be okay. I'll walk you through it, you know. But this is the idea, is we'll say, what's the domain? They're asking us the domain, and we're going to say, what's any number I can plug in for x, such that when I plug it in, this whole stinking thing is still bigger than 0, or at least at 0, but not less. And so that it opens up the adventure. And so here we go. So adventure time. 72 minus of x squared minus x. I'm wanting that to stay at or above 0. Let's see if we can figure out what x's make that happen. And so you guys have done this on a couple of tests by now, solving inequalities of quadratics and other kinds of things. And so this will be reminiscent of those approaches. I'm going to go a little bit fast so we can get you to break on time, but I at least wanted to kind of walk you through so that you're not totally like at a loss when you see this in your homework, you know. At least you'll have seen it together with us. Maybe we could be like, well, here's 72, and then a minus. Maybe before we do anything, we'll just distribute that minus so we don't have those parentheses, you know, and it'll be like minus x squared. Then on a minus of a minus is a plus x. That'll be good. From there, it seems like, well, this is a quadratic. They have an x squared and an x in it. Maybe we'll do stuff like we do, get it to factor or something if we can. It's a little weird being out of order like that. So if you don't mind, I'm going to put the minus x squared first. Then we'll put the x, and then we'll put the positive 72. Then it'll be a little bit more like what we're used to. It's super funky, though, having a negative on the x squared. I'm going to ask you guys for ideas on that one. How would you guys go about this if I didn't want the negative in front of my x squared? What would you guys do?
Take out a negative.
Sure, that might work. I was thinking something along those lines myself. And so there's a bunch of different tricks you guys can do. But I think that we'll go along the lines of something like Jude was saying. It's just, we'll just do a negative trick and it'll change the signs of everything. And so whether you be timesing a negative to both sides or dividing it to both sides or just factoring out a negative from this and then dealing with that separate, we'll probably just do a sign switch dealing with negatives. And so pick your favorite approach. Here's one that maybe everybody would be comfortable with. If we just divided everything, both sides by a negative or something, again, but whatever approach you want is fine, but just somehow it'll be a sign switch. If we divide everything by negatives, what's cool about this is that, well, 0 divided by anything is still 0. So that's not an issue. You know, we don't lose the 0 part. And then whether you do it this way or another way, a negative into a negative or a negative times negative, or if we pull out a negative, it's all going to sign switch everything. So a negative into a negative would be a positive x squared, then a minus of x, and then a minus of 72, minus of 72. And then you may have noticed that I left this inequality kind of sitting there because we were thinking about that. What do you guys remember about this? If I were to, you know, since we times are divided by a negative, what happens with the inequality? Anybody remember?
It flips.
Yes. We got another one for Jude coming in. There we go. Anyway, and so just remember that. But what that does is at least we have something that's a little bit more friendly for us that I think will actually even factor. So that's nice. I don't think we have to go quadratic formula on this or anything. So okay, guys, I need 2 numbers. Help me find 2 numbers. They got to times to negative 72, but they got to add up to -1. What am I thinking?
8 and 9.
That might work. Okay, let's do 8 and 9. Who gets the minus on that?
8.
Let's see if we did -8. I think it might be the other way.
Yeah, 9.
We need yeah, because we need a -1, right? So let's try it. Let's see it. What if we did +8 and -9? Those times to what we need. And then +8 take away 9. Yeah, that's a -1, right? Looking good. Although, as you guys know, that's about to switch up. And so, guys, tell me this. If I'm looking for a criteria of all this stuff, to just get it to be 0, that would be kind of maybe the first part of this. You know, we're looking for what makes it be exactly equal to 0. And that's where these standard numbers keep coming in. And then we'll try and figure out the inequality part. What number +8 makes 0? Anyone? Anyone? Some number +8 makes 0.
-8.
Yes, it's -8. This is almost a Bob Barker looking microphone, actually. Even though it's not a microphone. So we have, what do you guys say? -8 +8 will do it. And then again, of course, +9 take away 9. Now, these guys would make equal 0, equal 0. They take care of the equal part. As far as the less than part goes, we're going to keep this inequality around so we can, so we can make use of it. But we've pinpointed a couple of answers that make it equal to 0. And so you guys might remember how this goes. And I'm going to, again, give you a quick take on this. Whoa. From there, guys, we'll be like, well, okay, we found out that -8 and +9 do the trick to make this expression equal 0. And that's good because equal 0 is part of the solution. So I'm going to go ahead and color them in. Then we got to figure out, well, what kinds of numbers can we plug in that actually make the expression equal, not equal, less than 0, you know, which would be equivalent to the other expression being greater than 0 if you want to plug in up there. And so then that's where we're in this mess where we're like, well, I guess I'll just try some things, you know. So numbers anywhere from -8 out to infinity minus. What's something that's to the right? I mean, to the left of -8 over here that I could try.
Negative
What's,
9.
yeah, we got -9, and then we could try stuff there and try stuff there. What is the number that's to the right of +9 that we could try, guys?
10.
Yes. And then, what is a number that's in between -8 and +9 that we could try?
1.
Yeah, that would be fine. We could try a 1, or you could even do a 0 if you want. But pick, something nice and user-friendly, nice and easy for yourself if you can. So that'll be a good one. And so then we just try them, and then we'll see. And so if we try -9, then we will see what the behavior of numbers on this side of that -8 look like. And so let's see here. If we try -9 into this expression that we've boxed in, that'll be here over here. -9 plus 8, and then -9 minus 9. And we're wondering, is that going to give us the less than 0 we're looking for? Question mark, is that less than 0? And so let's see, if we do -9 plus 8, that's a -1. -9 minus 9, that's also big negative, -18 or something. This is a negative times a negative. And that seems to highlight what the behavior of things over here to the left are. If I plug in things that are to the left of -8, it seems like because they're bigger than negative, or bigger than 8 to the left, we'll end up with things that just end up being negative times negative. Now tell me, guys, negative times negative, is that going to be less than 0?
No.
No, it ain't, because we know how that works. Negative times negative is a positive. That's bad. Negative times negative, no. That's positive, not what we were looking for. Oh, well. So over here, not working. And then we try the same thing over here, and we'll be like, well, what about numbers that are in between there? -8. Oh, wait, no, what was it? Oh, we were going to try 1. So we're like 1 plus 8, and 1 plus 9, -9. And then these ones behave more differently. And so 1 plus 8 is +9. 1 take away 9 is -8. And then that kind of lets us know what the behavior of numbers like this look like. It's positive times negative when you plug stuff in between there because of how big the numbers are. And so positive times negative, that is negative, that is less than 0. Positive times negative is less than 0 because it's negative. This is, yes, this is good for us. So then we're finding out, okay, not only do we have solutions at 8 and 9, but we also have solutions in between the two of them from 8 to 9, -8 to +9. That's good. And then for the sake of time constraint, just pretend like I plugged in the 10. 10 plus 8 and 10 minus 9 ends up being positive times positive or something like that. It's not less than 0. And so that one's out too. And so what we end up with in this case, guys, is really the solution set is just the numbers from -8 to +9. Those are the only numbers in our domain, which is a tiny little stretch. And so when they ask you, like, what's the domain, then you could finally just tell them, so domain is just anything from -8 to +9, interval notation style. No infinities about it, although there's still infinitely many numbers in there. It's whatever. Anyway, so it's a tiny domain. Just remembering that a domain is the set of all the numbers you can get away with plugging in here. And that means that most of the number line over here and over there, I can't get away with plugging into this. I can only get away with plugging in numbers that are in between the 8 and the 9, including the 8 and the 9. Ta-da, da, 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 da. That's pretty cool, I guess. All right. Time to pause the recording. I'm going to give you guys a break here for a second. Oh, yeah. There we go. We just resumed a recording. Hopefully that hadn't been off for like hours. I think I've been remembering to get it back. Okay. So dig this, though, about inverses. an inverse of a function is sort of another function that undoes what your original function was doing in the first place. Check this out, inverses, inverse. Whoa, functions. I'd like you guys, before I finish that word, to notice how my U and my N are almost identical here. I'm not really sure how this happens, but we're going with it. Functions. There you go. Your mind will complete the pattern. You can ask the Gestalt people about it, or not bother to. Okay, so dig this. Inverse function, something's, let's put an S on it. There you go. So check this out. Suppose I had this, guys, f of x, take f of x, and it was like a real simple function that takes the input x that you put into it, and it just adds 5. So f of x equals x plus 5, that's all she wrote on that one. Then an inverse function would be a function that undoes what that one does. So, well, maybe we should get some notation down. Here, dig this. Suppose you have that. Here, no, scratch. Okay. Okay. If we took f of x as this, then we have an f inverse. We'll call it f inverse. Or it's typically written like this, guys. The way we say it is still f inverse, but it's f with a little -1. Sort of reminiscent of like multiplicative inverses with the -1 power. It doesn't exactly mean that, but it's like that. Anyway, f inverse of x just means it's the inverse of the function. All that's going to be is it's another function that undoes what this one did. So guys, tell me this. If I had a number, you know, and I'm plugging in numbers and I plus 5 onto all of them, how do I undo a plus 5? What would you guys say?
-5?
Yes. And so to undo, just like when we're solving equations here, to undo a plus 5, we'll minus the 5 back off. And that'll put us back to where we started from. If I put in a number, I plus 5 onto it, then I take 5 right back off, I have effectively undone the plus 5. And so that's what an inverse function does, is it's a function that you can take and you'd be like, I'm going to take every x now that I put into this function, and I will take 5 back off. It's a backwards version of the other function. It's the undoing function, or I don't know, it's a backwards of it, I guess, you know. And so this would be or at least one, this is a governing idea behind inverse functions. It's one of them that just undoes what the other one does. They kind of have opposite things going on. And so I chose a simple one on purpose, obviously, to demonstrate just the idea of it. And so also notice about it though, notice. Okay. Notice about these inverses though. What if we said this? Okay, f of 3. Meaning if I plugged a 3 into the original f function, f of 3 would be 3 plus 5 more. So whatever that is, 8 or something. F of 3 equals 8. Then also related to that, if only if kind of thing, we could say that f inverse acts backwards of it. And so let's make sure that that works. Tell me, guys, what would happen if I plugged in an 8 into f inverse? 8 into f inverse would be 8 take away 5. What do I get back out of it?
3.
Yes. And so we're noticing this about them. Not only is this a backwards version of the function, but it really does have the property that you might figure it would have, in that the inputs and the outputs, they switch, or the x's and the y's, they switch. Now the 8 was the x input, and the 3 was the y output, you know, instead of the other way around in the original function. And so that's something that we'll keep in mind about this stuff, is that in inverses, the x's and y's switch. The x's and the y's, they switch. Also known as the ins and the outs, they switch. Cool. But keeping that perspective in mind, because sometimes that's a good thing to keep in mind about it. It's a property of inverses. It's not how you define inverses. It's a property of them, but it really does help to keep that perspective around. An inverse is just a function that has the x's and the y's switched from the original one. And if you got a function that does that, you must have found an inverse. And actually part of your homework really is just getting used to that idea, because they'd bring up stuff like this. They'd be like, so suppose that you had a function that we were like, okay, some function, we'll call it g of x. No, not x. G of 5 equals 19. And they don't tell you what function it is. It's not necessarily x plus 14. It could be whatever. It's something. But somehow, if you plug a 5 in to the x, you get a 19 out for the y. Then they'll ask you this. They'll say, suppose that's true. Then riddle me this. G inverse of 19 equals what? You know, and that's all they'll ask. But I feel like you guys can handle this. If g of 5 is 19, then g inverse of 19, if I plug a 19 into the inverse of it, what should I get out of it?
Five.
Yes, we'll totally get a 5 out. I love it. Cool. Anyway, so that's the basics of this stuff. There's a little bit more to it over time. Let's talk about how to interpret this mess. Okay. Yes. Oh yeah, actually, no, still one more application of the basic idea. Sometimes you'll see this also. They'll be like, okay, suppose you have an f of x that's defined as follows. F of x gives, and they don't give you an equation to define it, but they just kind of womp. They give you a chart of the ins and outs of it, you know? Look how cool my chart looks. Guadalupe is like, man, I wish I could draw a cool chart like Adam does.
Yeah, I totally wish that.
Well, I figured. And Jude is like, I actually can draw a cooler chart than that.
No.
Okay. Dig this, guys. They give you these charts and it'd be like X, and normally we do X and Y, you know. They're going to put a little emphasis on the function notation aspect. So probably a lot of the time you're doing X and F of X. Although I'm seeing some X and Y stuff go on too. So maybe, I guess it'd be okay to do X and Y here. Either way about it, though. It's whatever. Okay. And then they'll just give you this, and they'll say, suppose f of x is this, and they'll give you a bunch of stuff to plug into it. 1, 2, 3, 4, 5. I feel like I've overdone this. 6, 7, 8, 9, whatever. Bunch of inputs, and then the y outputs are like, you plug in a 1, you get out 23. You plug in a 2, you get -7. You plug in a 3, you get 1. You plug in a 4, you get 80 or something weird, etc. ... I did way too many of them. Then they would simply ask you, this is what's coming your way. Then they'll say, okay, then f inverse of x gives, and then you got to come up with f inverse, and they'll do it as a multiple choice thing. So you don't have to draw. Oh my goodness. Okay. They'll give it to you as a multiple choice thing, so you don't have to come up with and draw your own stuff. Stop it. Although it'd be cool to draw your own. We all know this. because how cool mine is. But here's all they'll be asking for. Ta-da, 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 ta-da. Okay. Why can't I move that one anymore? There we are. Nope, not helping. Oh well. Okay. They'll be like, okay, give us an inverse here. And all you would say is this. Well, if in the original function f of x, 1 is an input and 23 is what you get out of it, maybe in the inverse then 23 is an input, and guess what number I would get out of it? This is where you guys guess.
Oh,
Remember?
a one?
Yeah.
Yes, it's exactly that. There's no figuring, there's no number crunching or algebra. You're just like, well, it's the other way, you know? And so you plug in this mess and you're like, well, I plug in a -7, I get out a 2. I plug in a 3. No, not a 3. I plug in a 1, I get out a 3. I plug in, what's the next one going to be? I plug in
80?
80 and I can get out a 4. Whoa. Etc. Stop it. Why is it acting like this? I've messed up my mouse. Okay. There we go. ... Cool. Dig in. Anyway, so this is just us re-emphasizing the basic idea about just a property of inverses, about them things switching, you know, a lot. Other things that come along with that, though, would be just some properties of inverses that we could look at. Okay, so dig this. Okay, now dig this one. We can juice this one for a lot more. Now that we're gonna have to start wrapping our mind around something, but we can still start with a chart. And so, dig this. Whoa. La 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 la. Go ahead and draw a cool chart with me. All right. Cool chart time. Now, okay. This time I do see him using the whole f of x terminology. It's whatever, or notation rather. And so dig this. Okay, let's start out and we'll just say like 0, 1, 2, 3, 4, 5. These are input numbers for x. And then the output numbers we'll be getting for f of x or just whatever. Okay, let's just do like 3, 4, 5, 0, 1, 2. Oof. Okay. Maybe before we get into inverses, let's remember how this works. If I were to say f of 2, that means I'm plugging 2 into the f function. What's the output going to be, guys, if I do f of 2?
5?
Yeah, just like we're used to. Nothing tricky about it. And then let's see here. Okay, what do you guys think about this? So f of 2 is 5. That's going like the function f, it seems to plug things from left into the right. You plug in from the left, it works over to the right, it goes that way. That's f. Now f inverse, of course, you know, is the other way around. It switches the x and the y's. It switches the ins and the outs. And so then if we were to say, well, okay, what about f inverse of 4? F inverse of 4, that's the idea of us saying, well, okay, now the output guy is actually the input guy. So this 4 is coming from the right-hand side as an output, a y guy, and it's working back to figure out, well, what number gave us that 4 in the first place? So if we're thinking f inverse, it's actually working to the left. You know, the outputs are now the inputs. So guys, tell me, working backwards, what number, if I backward work it, what number maps over to from 4 to the left there?
1.
Yeah, that'll be a 1. This is good. Yay. Okay. So then we're getting that down a little bit. Okay, so f of 2 was 5. That works over to the right. F inverse works from the right to the left in our chart because it's the inputs or the outputs now. And then, okay, a little bit of other stuff. Now back to working with just regular f, not f inverse. We know that's a left to right thing. But now we're saying f of some x value that I don't know, some question mark value. And then I know I ended up with a 3 as an output. They're going to tell you that. Suppose you had fx equals 3, then what the heck number was your x in the first place, you know? And so this is an f that works, it's the f function, it works from left to right. We're trying to figure out, well, what number here was that on the left that ended up popping over to a 3 on the right? What number here on the left ended up popping a 3 over to the right, guys? What number does that?
Zero?
Zero?
Yes, 0 does that. And so then giddy up, then x must be 0. I don't know, always circle the answer or something. And then similar questions will be asked even of the inverse function. And so we just have to be careful. We're saying f inverse of x, f inverse of some number, remembering that inverses work from right to left, you know, in our chart here. And so we're saying f inverse of some x value, don't know what it is, but I know that when I f inverse it, I end up with, say, a 5. F inverse of some number is 5, then we're going to figure out what the heck x number it was in the first place. So then we're like, oh, I know how f inverse works. F inverse works, but it takes numbers from the right and pushes them to the left. So what number on the right ends up pushing over to the left to give you a 5 out of it that way on the left?
A 2?
Yeah, 2 does that. Then x must be 2 because f inverse works that way. And so, cool. A 2 is the number that ended up being a 5 or whatever. Okay, cool. That being the case, I'm going to give you guys the same chart, use the same chart. And I have new challenges for you. See what you can do with this. Your turn. Figure for me a few of the same things. F of 3, f inverse of 1, f of some x equals 0, 4 equals 4. So x equals what? Also, f inverse of some x equals 4. So x equals what? See what you guys can do with that. Santana, I'm pretty sure, yes, I think I'm recording this time. Oh, you asked me that a long time ago. We're cool. Katya's here. It looks like we're good. Right on. Ashley Stuckey. You microphone working and stuff, you there? Ashley. She's thinking about it. She's just been having trouble getting this thing to connect is all. It's cool. Well, anyway, let me know if you get that thing set up, but at least you're here, so that's good. Okay, guys. I am recording this, right? Right? Let's see.
Yes.
Yeah, I started it
Uh-huh.
again. Yeah, okay. Yeah, we're good. Okay, thank you. Okay, so then, all right, back to the drawing board. Here we go. So f of 3, let's see if we can figure these out. F of 3, that means start at 3 and then point it to the right. That looks like we're going to 0. So then f of 3, I'm getting 0 on that one. And then, whoa. And then f inverse of 1, that means we're going from right to left. Inverse goes from right to left. So that's start at 1 and then backward over to get 4. Okay, now f of some x equals 4. So let's see here, f of some value on that. Now this is regular f, so it's mapping from left to right. So some x value that ends up mapping over to 4. That looks like this one heads over to 4, so it must have been a 1. So x must be 1. Pretend that says 1. And then f inverse of some x ends up being a 4. Let's see, that means f inverse of some x, as we map it over to the left, from right to left, there was some inverse value that ended up giving me a 4 as I mapped it to the left. And we've seen that one already. That was a 1 that did that. Boom. So we're getting a lot of 1 and 4 action going on. Cool. Well, it's pretty cool, I guess. And then there was one other thing I wanted to talk to you guys about while I still got you. Right on. Looks like Stucky's in the game. All right. Dig this. I keep on trying to keep on checking on the old chat here. Got it. Check this out about inverses. Suppose I had here, take this, take f of x equals, and then we'll start small, like 3x plus 5 or something like that. We'll have to move a little bit fast because I know we're running short on time. But take f of x equals 3x plus 5, and we're like, I gotta figure out f inverse of x. F inverse of x, equals whatever, and then that's answer box stuff. That's what they're looking for. Can you give us an inverse function? If they define the function by an equation, can you figure out an equation to describe the inverse of it, And so remembering that an inverse is a function that it undoes what the other functions do. And so I guess if we were looking at this, we would say, just like we were staying at the onset of it, a plus 5, I could undo a plus 5 with a minus 5, So my inverse at some point should have a minus 5 in it. Also, guys, what do you think about this? This thing has an x times 3. There's a times 3 involved in it, though, also. How do you undo a times 3? What's the opposite of a times 3? How could you undo a times 3? What do you guys think? What? Say it again?
Divide it?
Yes, that'll work. Okay. So if we're to come up with an inverse function, it should look something like this, but it should have probably a minus 5 in it instead of a plus, and it should also have probably a divide 3 in it at some point instead of a times. The only other thing to keep in mind is the order of operations. We used to do a socks and shoes principle, where it's like whatever layer was put on last, that's what you got to take off last. You got to take off the shoes before the socks. We don't got time for all that right now. What I would recommend is this. Here's a dirty cheater's approach to getting inverses, especially since we're down to the less than 10-minute mark. Remember about inverses is that they have this property where the x and the y are all switched. So what a lot of people do is they'll be like, oh, f of x equals 3x plus 5. The cheater's approach is they'll be just like scribble. I'll call this a y because, f of x we can call a y instead. It just depending on how you want to think of it. And then once I put it as a y, it's easier for me to see that I can get an inverse by just straight up switching them. You don't have to switch the particular values because we're trying to keep this in equation form and all that. You just switch up the variables they sell. And so in this case, we'll be like, well, I'll switch them. And so instead of y equals 3x plus 5, we'll put x equals 3y plus 5, you know? And then it's working, you know? And so then from there, it pretty much you have a functioning inverse. It's just, it's not in function form yet. You know, it's not explicitly in terms of x like we like to have functions. And so we'll have to like work that out. But as far as like having something that works as an inverse goes, we got it, you know? We got something that kind of does because we have, it's kind of guaranteed in the fact that the x and the y are switched. And that's a fundamental idea behind inverses, you know? It's a property of them. I don't know if you guys can hear the airplane. Anyway, so tell me about this. We're good at solving equations. Let's get that y by itself until it says something about x. How do I get rid of the plus 5, guys?
-5.
Yeah, there's the -5 we were talking about that we expected to happen. So now we got 3y equals x, take away 5. And then you guys know what to do. How do I get rid of the old times 3?
Divide 3.
Yes. Now we're cooking it. And now we got y by itself equals x, take away 5 and divide 3. And that's the inverse we were looking for. That is the inverse that undoes what this one does. Instead of saying times 3, then plus 5 on, this is the one that takes the 5 right back off. And then it untimes the 3 or divides the 3. That's an inverse. And so that tends to be our approach with these. Even when they get weirder, you'll tend to handle them by just being like, well, I'll switch the x and the y, and then I'll just solve it out best I can, you know? And like there are weirder variations of this, don't get me wrong. We don't have much time, but I wanted to at least go over a couple other funny variations with you. So let's take a couple more. Let's say g of x equaled, and it was like 7x, we'll do like to the third plus 8 or something. 7x to the 3 plus 8. And then we got to figure out g inverse. Also, we'll do an h of x equals, and it'll be like the square root or something, or the 3 root of x minus 5 or something weird. And we'll have to figure out h inverse. And that'll probably take us to the end here because we got very little time. Anyway, sorry we don't have time to practice this, but at least we can talk through it once through. And so remember how this goes. To figure out an inverse, we'll take it over to the side. We'll be like, you know what, I'm calling this a y, and then I'm going to switch them. We'll call it a y, and then we'll switch them. So then it'll be x equals 7y to the 3 plus 8, and then we'll just solve that out, you know? Tell me, guys, how do I get rid of the plus 8?
-8.
You know it. X take away 8 there equals, and then the 8's are gone, but we still have 7y to the 3. How do I get rid of that times 7?
Divide 7.
Yes. We'll divide to 7. And then we have y to the 3 equals all that mess. X take away 8, divide 7. And then finally we're down to like, it's almost y by itself. I just have this 3 power. Anybody remember how to undo a 3 power?
You square root it?
Yeah, it sort of is. It's very good. She's on a roll. It's at 3 power, so we'll 3 root it. And then we'll 3 root the other side. And then the 3 root and the 3 power undo each other. And what we've been left with is just a y sitting there now. Equals all that other mess, which is a big 3 root over x take away 8. Or I mean, yeah, whatever. And then x take away 8 over 7. And that's how the cookie bounces. And so let's see here. We got the old 3 root, x take away 8 over 7. That was the inverse we were looking for. And it had everything backward of what we would, what we were looking at before. The plus is a minus, the times is a divide, the power is a root. It kind of works out. And this way we kind of ensured that we had the order of operations backwardized too. Okay, same idea. This time we'll say, okay, this is a y, and then we'll switch them. And then let's see here. That's an x equals 3 root of y minus 5. Let's see here. What's weird about this one is that the 3 root is the absolutely outside layer. So that's probably what we should take care of first. And so Help me out, guys. How do I undo a 3 root? What do you guys remember? Any ideas?
Would you cube it?
Yeah. It's a cube root, so we'll cube it.
Mhm.
3 root gives us a 3 power, we'll undo it. Because just like on the last one, that 3 power and the 3 root, they undo each other. And so then we're just left with the y minus 5 sitting there equals x to the 3 on the other side. Looking good. And then you guys know what to do here. How do I get rid of that minus 5?
+5.
Yeah. Plus it. And then we got y equals x to the 3. X to the 3 plus 5. That's the inverse we were looking for. X to the 3 plus 5. Cool. Looking good. We got some inverses going on. Anyway, there are some other variations as time goes by. There's other stuff involved in both of these sections for composite functions as well as for inverses that, you know, we can't touch every detail as we go along the way. So make sure if you get stuck, check out Adam's take on anything that's evading you, if that's the right verb. And then
Quick question.
no questions.
How do we access this recording?
Progress reporting. You
No,
mean like for EOPS or what?
No, how do we access the recording, this recording?
Oh, the recording. She's like, no, listen to me. No, so this thing automatically will save in Zoom somewhere, and you may have a copy of it on your side. But eventually, the idea is that I just once it gets finished loading and stuff, I'll transition it into some kind of a YouTube video or something like that, and I can just give you guys the link to it.
Okay, awesome. Thank you.
Yeah, right on. Cool. Let's see here. Boom, boom. One more thing in there. Yes, as a matter of fact, I did find out. Oh shoot! I just did something. Where's it at? There we go. Okay. I finally made alternate versions of the first 2 tests. If anybody needs to retake either one of them, let me know. Just contact me on the side, and we'll figure out a good way in time to get it done. There's a message about that, and so I figured everybody could use it. And so if you're feeling like you struck out on either one of the first 2 tests, let me know, message me about it, and then we'll just figure out a good way to do it. Right on. Cool.
Cool.
Sick. In that case, let me stop sharing this whiteboard. I'll see y'all later, Vader haters. You doing good?
Alrighty. See you later.
Yeah. Up and out. Right on.